What you're seeing in this video clip is the power of an uncontrolled nuclear fission reaction. At GCSE, a nuclear fission reaction is described as when a heavy nucleus splits into two smaller daughter nuclei through the absorption of a thermal or slow-moving neutron. Once it splits into two daughter nuclei, it releases 2 or 3 more neutrons and a lot of energy. In this process, a chain reaction can start. This chain reaction is essentially controlled by how much fuel you have. In this video clip, they weren't sure whether the fission bomb itself would go on to react with neutrons in the atmosphere and just continue burning up the atmosphere. We now know that doesn't happen, but the truth behind nuclear fission still stands, that in a nuclear fission reaction, when it's uncontrolled, a lot of energy is released. We can harness this through controlled nuclear fission reactions, which tends to be covered in your specification, or we can cause a lot of destruction through uncontrolled nuclear fission reactions, like in this video clip.
This simulation shows a nuclear fission reaction. When I press the red button, I fire a neutron into the uranium, which becomes uranium-236, and then splits into 2 daughter nuclei and 3 more neutrons. That Men in Black gun doesn't exist, by the way. It's just for the sake of the simulation. Now, here on this tab, I'm just going to do it one more time. We're going to now try and make a chain reaction like we discussed for the bomb, whereby we add many uranium-235 nuclei in a closed chamber, and we can see what happens. You can see that the daughter nuclei, they stick to the container, and that's why the nuclear reactor container in itself, when we generate fission energy, has to be disposed of appropriately, because those daughter nuclei are still radioactive. But you can see the chain reaction happening here. The neutrons are going off and finding more uranium nuclei and making a larger and larger amount of energy. And this is a nuclear power plant sort of design. This is a controlled fission reaction. And what you should see is the energy starts going higher as the neutrons are released. But as you put the control rods in, the control rods absorb the excess neutrons and the reaction decreases. Oh, okay. Straight into a past paper question. Okay, so I'm just answering a past paper question here. As you can see, I am writing it as I'm speaking. This question's around nuclear fission and nuclear fusion. And in question 1, it's just asking you for a man-made type of background radiation. So that's just leftover radiation that's sort of like left in the atmosphere as a result of what we've done as humans, really. So you've got a choice with this. Obviously, nuclear weapons, Chernobyl, medical equipment such as X-rays, etc., etc., etc. They all contribute to background radiation. And then for the second one, the 2 main types of nuclear fuel are uranium. That's generally used in power plants, for example, like Chernobyl used uranium as its fuel. Plutonium is what they were using in that uncontrolled reaction that you just saw on the video clip we watched. So uranium tends to be the one that's used more often. And now, based on what we've done in the video, hopefully this question should be relatively easy for you. Describe the process of nuclear fusion. Describe the process of nuclear fission. And so we can see that we've mentioned all the key words here. Like I said, sometimes they want you to identify that it's a slow-moving neutron, but in this specification, just a neutron is fine. Neutron absorbed is fine. The nuclear splits, though, that's got to be in there. It splits into 2 daughter nuclei. And as we've already said, it splits into 2 or 3 more neutrons. And you might be like, well, why is it 2 or 3 more neutrons? It kind of really just depends on energy distribution, really. So you don't need to understand why it's 2 or 3 neutrons, but that's just what you write. So generally speaking, within a nuclear fission reaction, there'll be sort of 2 or 3 more neutrons released in that reaction. And like I said, the rest of the question just then goes on to explain here that some gamma rays can be released as well. So again, it's a bit of a spec thing, this. Some gamma rays can be emitted because the daughter nuclei are still radioactive. So like we saw in the simulator, if they stick to your the insides of your sort of like nuclear reactor, they can still be giving out gamma radiation. And now it's asking us to compare to nuclear fusion, which isn't covered so much on the specification. But how this works is you get 2 light nuclei, they join together, they make a heavier one, and that actually releases more energy per kilogram than nuclear fission does. This is essentially based on Einstein's equation, E equals mc squared. And you can see here, some mass is converted into energy. You don't need to talk about E equals mc squared in the GCSE spec, of course. But that's nuclear fusion. And now it's asking about explain the advantage of the radioactive waste that comes from the reaction, having a shorter half-life, why that's beneficial. Well, what you've got to remember, when it comes to, let's say, having a kilogram of radioactive waste, the faster it decays, let's say, so it's decaying, the faster it decays, the less radioactive nuclei there are to decay later on. And it's an exponential decay curve. So what that means is if you have a really high rate of activity, a rate of nuclear decay at the start, it's more dangerous right at the start, but then over time, it becomes much less of a risk over a greater amount of time. So the risk of harm decreases quickly. And that is that.